Welcome! In this series of short videos, we will look at topics common to both the PowerBasic console and Windows compilers. Today we will look again at a contact simulator, using a graphics window and graphics commands. In this video, we're going to revisit the code we created a couple of months ago to create a contact simulator. Today we will be expanding the application to take account of isolation and limited immunity. This is a contact simulator that allows you to monitor a number of houses or social environments and the people that live and work around them, tracking contacts between them and possible infections and how they might spread. I'm not an epidemiologist, but I thought that looking at how an application might be developed to simulate the spread of infections would be a good way to demonstrate some of the things that PowerBasic can do with graphics windows and graphics commands. I'm briefly going to mention what has been added to monitor isolations and immunities, and then launch the application. The source code, as always, will be uploaded to the GSF software website. The link is in the description below. Here we see on screen the code. All that we have added to this code is we've expanded on the user-defined type for the people array. We've added 3 extra elements. One to track the R number by keeping track of the number of people infected by this particular person. The days immunity left to record how many days immunity this particular person has left if they are immune. And the period that isolation started. These extra entries in the dataset allow us to track immunity and isolations. In addition, we've added a number of new constants to help us track this. There's now a constant so you can adjust the chance of catching the infection, a constant for the number of days of immunity that someone will have after they come out of isolation, and a flag to allow you to turn on or off the isolation mode. If use isolation is false, then isolation will not kick in. The periods until isolation is the number of time periods, after which, if the use isolation flag is turned on, the person will be isolated. So we'll do a quick compile, and we shall now run our simulation. Now, as in the last video, the simulation starts with a small number of people infected, 5 in this case. We have 3 in the brown area, 1 in the red, and 1 in the green. Now, they won't start infecting people until halfway through the first day. Now, while we wait for that to happen, we've expanded the graph slightly. We've put a number scale on the top graph, which records 2 pieces of information. First, as you can see now, the number of people infected is shown as a red column. The red house and the brown house are both heavily infected now. As we move on to day 2, what it will show is a green line in the top chart telling you how many people that day have been infected. The infections per house graph is showing the percentage of each house that are actually infected at this point in time. You'll see in the top graph now the green line is showing how many infections were on the first day and how many infections so far on the second day. This way you can gauge whether the number of new infections is going up, down, or remaining the same. At the very bottom of the screen we have the constants. Total number of days in the simulation is 14. We'll now see that the isolation is kicking in. You'll see that on the main screen that the people who are infected are starting to disappear from the main screen. And the number in isolation is going up. This means that the people are now isolated and cannot infect anybody else while they're in isolation. The system is set at the moment to allow the people to recover after 2 days. And after 2 days they will appear back on the main screen and they will be then immune for 2 further days. So we're well into the first wave now, with the majority of people having been infected. As the simulation continues, the social distancing between people will become larger, and therefore the chance of them being infected will go down because they are social distancing. In the bottom information section, we're showing the R number, which as you see at the moment is going down. You'll see that the number of people infected is decreasing because people are now recovering, and having been recovered, they will be removed from the isolation count and moved back onto the main screen. Now these people are immune for, at the moment, 2 days. So even if they do become close to someone who is already infected, they will not themselves become infected. So you'll see we're now past the first peak. The number of infections per month is gradually going down. So using these constants, you can actually tweak how the simulation runs. You can increase or decrease the chance of catching the virus. You can set the initial number of infections to be higher. You can change the recovery, and you can change the isolations, as well as the number of days of immunity. Now if we look at the main screen now, we will see that there are very few people actually infected now. There are quite a few in isolation, and after they come out of isolation, they will of course be immune for 2 days. So if we look at the total number of infections per house, it's certainly looking quite good, because the number is gradually going down. The purple area had the highest number in isolation, and it's now going down. We'll see that now we're past the first spike. There are people who have been infected, recovered, stayed immune for 2 days, and are now being reinfected if they become too close to someone who already has the virus. So the purpose of making these changes to the application was to see how putting people in isolation would change the trend. As we see now, we're well past the first peak. There are more people being infected now, so the number of infected is rising. And these will gradually go into isolation after 1 day's infection. However, the second peak in every simulation I've run is never as high as the first peak, because there are more people on the board who are immune at any point in time, albeit only for 2 days. And as time does go on, the people on the board do become further apart. So on the main board, we'll see that some of the people on the board are quite well isolated from everybody else now. Therefore, their chance of actually catching the infection is minimal. However, there are a fair number of people who are very close together, and while their immunity lasts, they will be fine. but as immunity is only set to last for 2 days, unless they move further out, there's a very high chance of them being infected again. So of the 150 people on the board, we have about 50 currently infected. So that's an infection rate of about 30%. Now, the one house or social area that seems to be doing best is the light blue area, because at the moment, the majority of their people are not infected. And those that are quite some distance away. So this augurs well for them, as long as they don't get too close to some of the people in the brown area who are infected. And they are doing that now. So the one thing isolation seems to give us, it seems to flatten the curve considerably. Although it does not completely eliminate the infection. So we are now on day 9. And by the numbers, it looks very much though as though the second wave is actually flattening out now. The number of new infections is being balanced out by the number of people who are recovering. So we're managing to stay just under the 50 people infected. And as we move on to day 10, you'll see that the board is now more socially distanced than it was in days 8 and 9, thereby reducing the number of people who should in theory get close enough to catch the infection. Looking at the green graph at the top, it certainly looks as though we have had the second peak and we're now either leveling out or edging up slightly. This could well be the third peak we're into now. And again, we haven't gone over 50. Well, moving on to day 12, I would say this is certainly the third peak. And it does appear to be slightly higher than the second one. But again, not nearly as high as it was on day 2. We have about 30 people currently in isolation. And obviously when they come out of isolation, they will be immune for the last 2 days of the simulation. So again, the amount of social distancing going on is considerable now. And the infections are mostly set. And we're definitely leveling off on the third peak. And now as we move into the final day of the simulation, looking at the graph, the number of people infected per day is going down. So in the simulation we appear to have had 3 peaks, an initial high peak and 2 subsequent peaks, the middle one being lower than the last one. And we're still hovering just over the 50 people infected. So all in all, we've stayed fairly steady for a few days now, of around 30%. 30 to 35% infection. And that's the simulation completed. Now we can have a look at the code. As I said, the main changes are to the people array, where we've added 3 extra elements to the dataset, and the use of the constants. If we have a look at the processing, we'll see that at the beginning of the processing we're opening a graphics window. We're then using the attach command to attach the handle we picked up from using the graphics window command, and we're setting the redraw option. The redraw option is an important one because it allows you to draw things to the graphics window and not display them on screen until you tell the system to redraw the entire screen. This radically improves the performance of the system. To redraw the window for every tiny change you wish to make to it slows the system down considerably. We're also setting the graphics scale. This allows us to set the scale of the window so that the actual size of the monitor you have is quite irrelevant. Since we're using a fair number of random numbers, we're going to randomize the system with the timer, which gives us as close to a pseudo random number generator as we can get. The setting up of the screen hasn't changed from the last video. We're setting up the number of colors, placing the houses on the screen, prepping the people, and then outputting the initial results to the screen. And then we're running through the simulation from the first day to the maximum number of days. So it's quite possible to increase it beyond 14 days if that's what you want to do. And within each day we have a number of time periods. In this case about 1500 a day. And this next line is an important one to put into your code. If the window is closed and is no longer there, then this exits the loop. If you didn't have this line of code in here, then what would happen is your graphics window would close and it would appear as if the application had actually finished. But the application would still be running in the background, just not showing you a graphics window. Doing this allows us to come out of the loop and finish off the program, closing it down and freeing up all the memory you've used. Now, the output results is the routine which actually draws the current state of play onto the graphics window. We also have in here a move to isolation. This is new. This moves people to the isolation if they haven't been affected long enough. And then we move the people. And at the end of each day, we reduce the immunity. That way, if someone actually is infected, gets put into isolation, and then comes out of isolation, they will remain immune for the number of days you've set in the constant, which is currently 2, and then at the end of each day we reduce the immunity by 1. Quite simply by running through each element in the array of the user-defined types for the UDT people, looking for those whose days immunity are greater than 0, and using the decrement command to reduce it by 1. The simulate movement command is very close to what it was in the last program. This one works out which direction the person is moving. What we've added is we have put a constant in so you can actually set the chance of catching the infection. Now, we set it at 60%. If you set it at 100%, then obviously as soon as they get close enough to someone who's infected, they will pick up the infection. Reducing it below the 100 means they can get close briefly, but not for too long. And we're using the turn infected to pick up the day number multiplied by the maximum number of periods, which basically works out the period they were infected. There are a number of new routines to work out the number of people in isolation, which is basically running through the same array and doing an increment for the number of people in isolation. This is used to redraw the screen. If we have a look at the output results, you'll find this is very similar. we've got a new array in here for the number of people in isolation. And the graphs are as before, the only difference being we've actually put some numbers on the axis to make it a little easier to see how many people are infected. These are our vertical tick marks. This is using the graphics line command with a bit of arithmetic to draw the lines and setting the position so you can actually print in the number. The rest of this hasn't really changed. We've just put in an extra thing at the bottom to put in the isolation box. This is a straightforward graphics box, drawing on screen just exactly the same as all the others, with a blue border and black in the centre. This just prints out for the number in isolation in each of the houses. The only thing I've done in here is I'm using the graphics color command to set the color dependent on the house, so that the people in the blue house will be printed as a blue number. And then at the end, the information box. This is only changed to move the lines slightly closer together to give us more room to put all the constants on the screen. For example, we're putting a new constant in for the calculation of the R number, and I've created a function to return that number. All this one is doing is it's sweeping through the people array, picking up which ones are actually infected, incrementing a counter, and then checking the infections today, and a simple bit of arithmetic to work out the resultant number. And the function returns that using the format command. So we always get at least a number before the decimal point and two numbers after the decimal point. So as I said earlier, you feel free to download the source code for this application from the GSF software website. The application will run either in the Windows compiler or the console compiler, quite happily. That's it for today. Thank you for watching.